Okay, welcome back to the deep dive. Based on the material you shared, we're diving deep into the quest for dark matter today, really exploring where the field stands right now.
Yeah, there's some really interesting stuff coming out, laying out the latest thinking.
Absolutely. And our mission for this deep dive is, well, to understand why many scientists feel there's a bit of a crisis brewing,
Mm,
why some of these long-held favorite ideas about dark matter are being seriously challenged, and, what genuinely new and exciting avenues are opening up.
especially, yeah, bringing in all this data from astronomy and the whole new window with gravitational waves. It's a big shift.
It really is. So let's unpack this. So right away, the sources talk about this growing sense of crisis in the dark matter community. What exactly is driving that feeling?
Well, it stems primarily from what hasn't been found.
Hmm.
For decades, there was a really strong theoretical preference for dark matter being a certain type of particle, particularly weakly interacting massive particles, or WIMPs.
Right, WIMPs. Heard a lot about them.
Exactly. But despite these just enormous experimental efforts to find them, and other popular ideas too, like axions or sterile neutrinos, we just haven't seen convincing evidence yet. It's been quiet.
Right. WIMPs felt almost, well, inevitable for a while there, didn't they? Why were they such a favorite idea?
They appeared almost too neat, in a way. They fit beautifully into theories that were actually designed to solve other problems in particle physics, like the hierarchy problem.
Ah, the one related to the Higgs boson mass.
Precisely. These theories often introduce new particles at what's called the weak scale, a specific energy range. And the fascinating part, the sort of magic, was that particles at this scale would naturally be produced in the early universe with, well, roughly the right abundance to account for all the dark matter we see today.
Okay, so it just kind of worked out perfectly.
Yeah, this idea that things just naturally fall into place without needing incredibly precise fine-tuning is what particle physicists call naturalness. And it was a core guiding principle for a long, long time.
Naturalness sounds intuitive, but it's a bit more technical in physics, right?
Yes, exactly. In this context, naturalness means a theory where fundamental properties like a particle's mass aren't extremely sensitive to um, quantum corrections from unknown heavier particles. If you didn't have new physics, these corrections could make, say, the Higgs mass balloon to an absurd size unless there's this almost miraculous cancellation of numbers happening behind the scenes.
Ah, okay.
So natural theories introduce new particles and symmetries like supersymmetry or CUY to avoid this kind of fine-tuning. And many simple CUY models specifically predict WIMPs as their dark matter candidates. That made them natural in this very specific physics sense.
And the issue is, despite this strong theoretical pull, this elegance, we haven't actually found the particle's naturalness pointed to.
That's precisely the challenge. Experiments, particularly at the Large Hadron Collider, the LHC, have searched intensely for these expected new particles at the weak scale predicted by theories like simple CUY. And so far, the only particle found is the Higgs boson itself, behaving pretty much exactly as the standard model predicted. No sign of Susie-White partners or other naturalness-motivated particles. The sources are pretty blunt about it. They
Yeah.
suggest this raises the possibility that these natural WIMPs might have been nothing more than an attractive red herring.
Attractive red herring. Wow, that's a pretty striking phrase. So, a key guiding principle like naturalness led us down a path, a very promising path. And when we got to the end of that path, the expected prize just wasn't there.
That's a really good way to put it. The null results, the lack of discoveries from searches for natural WIMPs, experimental data, is increasingly ruling out the simpler, most natural versions of these theories. It forces physicists to consider, well, how much fine-tuning are they willing to accept before the connection between theories like Susie-Y and dark matter, driven by naturalness, kind of loses its predictive power.
Okay, so if the natural WIMP idea is faltering because we haven't seen the particles predicted by those specific natural theories, does that mean WIMPs are completely off the table now? Should we just forget about them?
Not entirely, no.
Yeah.
The sources emphasize that if you sort of decouple the concept of WIMPs from the strict requirement of naturalness as the primary guide,
Okay.
then the idea of a WIMP becomes a broader category. It's simply a particle that got its observed abundance in the early universe through self-annihilations. The mechanism still works, potentially.
And how does removing that strict naturalness constraint change the search then?
Oh, it blows open the range of possible WIMP properties. Mass, interaction strength, everything. We're no longer restricted to that specific energy range around the weak scale. We could be talking WIMP masses from around 1 MeV, that's roughly twice the mass of an electron, so pretty light, all the way up to maybe 100 TeV, which is incredibly
Oh,
heavy.
that's a huge range.
It is. And searching this vast parameter space,
Mm.
eventually, the range of possible mass and interaction strength combinations a particle could have requires entirely new approaches, different thinking.
Different kinds of experiments, then.
Absolutely. For very light dark matter particles, say below 1 GeV, you need detectors designed to look for scattering off electrons. That's different from the scattering off atomic nuclei that the traditional large WIMP detectors mainly focus on.
Right.
You also need really novel detector technologies, things like superconductors, superfluids, or maybe exotic materials like Dirac materials, because the energy deposited by these light particles is just tiny, very hard to see.
And for these lighter particles, do they need something else to interact to get the right abundance?
Yes, that's a good point. To explain their abundance via annihilation, these lighter particles might need their own dark force carriers.
Dark forces.
Yeah, think of them like the photon is the force carrier for electromagnetism, right? But this would be a hypothetical particle that mediates interactions primarily between dark matter particles themselves. And these could potentially be probed by searching for new light particles produced in high-intensity but low-energy particle accelerator experiments. It's a different kind of accelerator search. Got it. So light WIMPs need small-energy, high-intensity searches, maybe looking for new forces. What about the heavy end of that expanded WIMP range you mentioned, like around 100 TeV? That's massive. Yeah, for those ultra-heavy candidates, you're looking for different signals entirely. You're typically looking for things like gamma rays produced when these massive particles annihilate in dense regions of space, like the center of our galaxy. Instruments like the upcoming Cherenkov Telescope Array, or CTA, are designed specifically to detect such high-energy gamma rays. So that allows us to probe the upper end of the WIMP mass range through what we call indirect detection, looking for the products of annihilation.
So it really sounds like WIMPs are still definitely being searched for, but the type of WIMP and the methods to find them have dramatically diversified once naturalness isn't the sole driver anymore.
That's exactly right.
What about the other popular candidates you mentioned earlier, like axions and sterile neutrinos? Are they still in the running?
Oh yes, they remain very active areas of research. Axions are particularly compelling for different reasons. They arise naturally in theories trying to solve something called the strong CP problem,
Okay.
which is another puzzle in fundamental physics, explaining why certain symmetries behave the way they do, and specifically why the neutron doesn't have an electric dipole moment that theoretically it seems like it should. The solution involves introducing a new particle, the axion. It solves that problem and could be dark matter.
Two birds with one stone, potentially. And how are we looking for these axions?
Well, experiments like ADMX, the Axion Dark Matter experiment, use really strong magnetic fields inside resonant cavities. The idea is to try and convert axions from our galaxy's dark matter halo into detectable microwave photons. They've already excluded a range of possible axion masses, and future runs and totally new experimental designs are pushing the sensitivity across a much wider spectrum, looking at both higher and lower masses. It's a very inventive, very clever experimental area.
Sounds like it. And sterile neutrinos, what's the motivation there?
Sterile neutrinos are mainly motivated by the discovery that regular neutrinos, the ones we know in the Standard Model, actually have mass. This wasn't predicted by the simplest version of the Standard Model.
Right, that was a big discovery itself.
Huge. So introducing sterile neutrinos, which interact very weakly with normal matter, primarily just through mixing with the known active neutrinos, is one way to give mass to the standard neutrinos. And if these sterile neutrinos are light enough and live long enough, they could contribute to, or maybe even be all of, the dark matter.
Has there been any potential hint for them? Anything intriguing?
Well, the sources note an intriguing, though still very debated, possibility. There's an unidentified X-ray emission line observed at around 3.5 keV in the combined spectra from multiple galaxy clusters and galaxies.
An unexpected blip of X-ray light.
Sort of, yeah. Some scientists have proposed this could be a signal from decaying sterile neutrinos. Now, the origin is still really uncertain and it's heavily scrutinized, lots of debate, but it's a definite target for future X-ray telescopes like eROSITA, X-ARM, and Athena, which will have much better sensitivity and energy resolution to check it out. Accelerator searches, like the proposed SHIP experiment, are also designed to look for sterile neutrinos produced in particle collisions.
Okay, so WIMPs, axions, and sterile neutrinos were historically the sort of big three particle candidates, guided by these theoretical ideas.
They were definitely the focus for many years, yeah. Largely guided by specific theoretical motivations like naturalness or solving other particle physics puzzles. But the lack of definitive evidence, especially for those simplest natural WIMPs, has really forced a fundamental rethinking.
And that leads to this new guiding principle you see discussed in the sources: no stone left unturned. That sounds pretty broad.
It is, exactly. It reflects a move away from relying too heavily on theoretical predictions or, frankly, biases to guide where we should look. Given the sheer vastness of possibilities for what dark matter could be, I mean, the sources talk about spanning something like 90 orders of magnitude in possible mass.
90 orders of magnitude. That's astronomical.
It's almost incomprehensible, from incredibly light wave-like particles to supermassive objects. So the new approach is to try and systematically explore everything, leave no stone unturned.
Okay, 90 orders of magnitude. What kind of candidates are in that absolutely massive mix beyond the traditional particles we just discussed?
Well, you're talking about candidates like ultralight fuzzy dark matter, which might behave more like a wave than a particle on large cosmic scales. Could be Bose-Einstein condensates filling galaxies. And then at the other extreme, really massive objects like primordial black holes.
Primordial black holes, like the kind of black holes LIGO and Virgo detect merging. Could they be the dark matter?
Potentially, or at least part of it. The observation of merging black holes by gravitational wave detectors definitely sparked renewed interest in the idea that some fraction of dark matter might be made up of black holes that formed in the very, very early universe, long before stars and galaxies even existed. Now, constraints from various astronomical observations, things like gravitational lensing, the cosmic microwave background indicate they probably can't make up all the dark matter across all possible mass ranges.
Okay.
But searching for a subdominant population, maybe black holes of a specific mass making up some of the dark matter, is still really crucial. And finding them would immediately tell us something profound, that dark matter isn't just a single type of particle.
How so?
Because you'd expect to see different signals, maybe like annihilation radiation, around black holes if dark matter was purely particle-based and clustered there. Finding primordial black holes would complicate the picture in an interesting way.
It really does sound like the search is broadening dramatically, not just in what dark matter could be, but also how we're looking for it. It's not just about building bigger detectors underground anymore.
That's the key takeaway from the sources, absolutely. Diversifying the experimental and observational effort is now seen as the most promising path forward. And a massive part of this diversification involves leveraging astronomical observations, looking up at the sky.
How can just looking at the sky help us find dark matter particles? That seems a bit counterintuitive, doesn't it?
It does at first, yeah. But astronomical observations offer a completely different window onto dark matter compared to laboratory particle experiments. Lab searches look for dark matter interacting, however weakly, with the particles of the standard model, the stuff we're made of, the detector material.
Right.
Astronomy, on the other hand, lets us probe how dark matter interacts with itself and how it shapes cosmic structures over billions and billions of years. It reveals dark matter's gravitational influence and potential self-interactions on truly vast scales.
So it's less about direct detection, like a particle hitting a target, and more about observing its large-scale cosmic behavior.
Precisely. One key property we can probe is whether dark matter is truly collisionless, meaning its particles basically just fly past each other, interacting only through gravity. The standard cold dark matter model, the sort of baseline, assumes this. But if dark matter did have significant self-interactions, if particles could scatter off each other,
What would that change?
it could potentially help explain some observed subtle differences between cosmological simulations and actual observations on small scales within galaxies, things like the Kuskor problem.
Where simulations predict really dense centers for dark matter halos, but observations sometimes show flatter density profiles.
Exactly that. Or the missing satellites problem, where simulations predict many more small satellite galaxies orbiting bigger ones like the Milky Way than we actually observe. Self-interactions could potentially smooth things out and alleviate some of these tensions.
Interesting. And how would we actually see evidence of dark matter bumping into itself out there in space?
Well, self-interactions could make the central regions of dark matter halos less dense and also more spherical than predicted by the purely collisionless models. So we can look very carefully at the shapes of galaxy clusters, using techniques like gravitational lensing, how their gravity bends light, and also by looking at the distribution of hot gas with X-ray observations. Then we compare these observations to simulations that include different amounts of self-interaction. This has already allowed scientists to place some upper limits on how strongly dark matter particles can interact with each other.
And you can see this in colliding galaxies, too.
Yeah, another really striking place to look is in colliding galaxy clusters, like the famous Bullet Cluster. In these collisions, the hot gas between the galaxies collides and slows down, while the galaxies in the dark matter, being mostly collisionless, should just pass right through.
So the dark matter and gas separate.
Right. If dark matter is self-interacting, though, its distribution might lag behind the galaxy slightly or be offset differently from the hot gas, which does collide strongly. Observing this kind of offset, or lack thereof, provides constraints, but it requires really complex simulations that accurately model the normal matter, the gas and stars as well.
That's fascinating, using these giant cosmic collisions as particle physics experiments, in a way. What other dark matter properties can astronomy reveal?
We can also probe the fundamental coldness of dark matter by looking for its substructure. If dark matter particles were moving very slowly in the early universe, truly cold and non-relativistic, then standard cosmology predicts a vast hierarchy of structure. Countless small, dense clumps of dark matter should exist within the larger halos of galaxies and clusters.
Like Russian dolls of dark matter clumps.
Kind of, yeah. A whole spectrum of sizes.
And if dark matter was, say, warmer than expected, or maybe made of much lighter particles,
Then its initial random motion, its speed in the early universe, would tend to smooth out density fluctuations on small scales. It would effectively wash out the formation of the smallest dark matter substructures. Fewer tiny clumps would form. We could look for signatures of this warmth or suppression of small structures in various ways. One key probe is the Lyman alpha forest.
Lyman alpha forest, that sounds cool. What is it?
It refers to the pattern of absorption features you see in the light from very distant quasars. As that light travels towards us over billions of years, it passes through intervening clouds of hydrogen gas in intergalactic space. These clouds absorb the quasar light at specific wavelengths, creating a dense forest of absorption lines in the spectrum. The statistical distribution of these absorption lines is very sensitive to the underlying distribution of matter, including dark matter, on small scales. So the Lyman alpha forest provides constraints on the mass of potentially warmer dark matter particles, or even ultralight fuzzy dark matter, which would also suppress small structures.
Okay, so analyzing light from quasars tells us about the clumpiness of dark matter. Are there other ways to spot these predicted small substructures, these clumps?
Absolutely. And stellar streams are an incredibly promising area right now. These are these long, thin trails of stars you see orbiting within galaxies, like our own Milky Way. They're essentially the debris left behind when smaller satellite galaxies or globular clusters get tidally ripped apart by the gravitational pull of the larger galaxy they're orbiting.
Like breadcrumbs tracing their path.
Exactly. And as these stellar streams orbit, nice and thin, if a small, invisible dark matter subhalo one of those predicted clumps passes nearby or even right through the stream, its gravity can leave a detectable mark. It could pull stars out, creating a gap or a dent in the stream's density, or maybe slightly perturb the star's velocities.
So you look for breaks or wiggles in these star streams.
Precisely. And upcoming large astronomical surveys, especially the Gaia Space Telescope, which is mapping the positions and motions of billions of stars in the Milky Way with unprecedented precision.
Yeah, Gaia's data is amazing.
It really is.
Yeah.
And also the Legacy Survey of Space and Time, or LSST, coming online soon at the Vera C. Rubin Observatory in Chile. These surveys will be absolutely crucial for finding and characterizing many more stellar streams and searching for these subtle perturbations caused by dark matter subhalos.
LSST, right. That's the one that's expected to produce just a phenomenal amount of data, isn't it?
It is. The sources call it an avalanche of data. And it's not just for stellar streams. LSST and other large surveys leverage another really powerful tool for mapping dark matter: gravitational lensing.
Okay, we mentioned lensing for cluster shapes. How does gravitational lensing help us map these smaller dark matter substructures?
Right. So when light from a very distant object, like a background quasar or galaxy, passes through the gravitational field of a massive foreground object, like a galaxy or cluster.
The gravity bends the light like a lens.
Exactly. This can create multiple distorted images of the distant object, or stretch it into arcs or even complete rings. That's what we call strong gravitational lensing. Now, the crucial part is, if there are small, invisible dark matter subhalos within that main lensing galaxy, or maybe even floating along the line of sight between us and the lensed object, their individual gravity can subtly perturb the paths of the light rays even further.
Tiny extra bends on top of the main bend?
Kind of. It changes things like the relative brightness or the flux ratios of the multiple images of a lensed quasar. Or it can introduce tiny wiggles or distortions in the shape of a lensed arc that wouldn't be there otherwise.
So you're analyzing these really small distortions in the lensed images to infer the presence of invisible dark clumps that must be causing them.
That's the idea. By precisely measuring these subtle effects, particularly these flux ratios in multiply-image quasars, we could potentially detect the presence of these dark matter substructures down to much smaller masses than we could ever hope to see through their gravitational influence on stars alone. And LSST is expected to discover literally thousands of new lensed quasars, providing a huge statistical sample for this kind of analysis. Other facilities like the Euclid Space Telescope, the Extremely Large Telescope, EELT, radio telescopes like LMA and VLBI, they'll all contribute critical high-resolution data too.
Okay, so astronomy gives us these unique ways to probe dark matter's behavior and distribution on large scales, its self-interactions, its clumpiness. That's a huge addition to the toolkit. What about the other new window mentioned in the sources, gravitational waves?
Right, the detection of gravitational waves, starting with the LIGO-Virgo observations of merging black holes back in 2015, has truly opened up an entirely new way to explore fundamental physics, and that absolutely includes the search for dark matter.
And how does detecting these ripples in space-time itself connect to the search for dark matter? It seems even more indirect, maybe.
Well, we touched on primordial black holes earlier. Gravitational wave detections are the direct way to find and study these potential dark matter candidates. The rate at which we detect merging black holes and their observed masses and spins, the properties we measure from the waves, can tell us whether a population of primordial black holes exists at specific masses and whether they could plausibly constitute a significant fraction of the dark matter. We can directly count them, essentially.
Okay, so checking the PBH hypothesis. And you mentioned earlier that gravitational waves have already impacted our understanding of alternatives to dark matter.
Yes, this is a really significant point mentioned in the sources. For decades, some alternative theories propose that maybe the effects we attribute to dark matter, like galaxies spinning too fast, aren't due to unseen stuff, but because gravity itself behaves differently on those large cosmic scales than Einstein predicted. Theories like modified Newtonian dynamics, or MOND, were attempts to explain observations without needing dark matter.
Right, modifying gravity instead of adding matter.
Exactly. But the gravity wave detections delivered a critical, really powerful test for many of these ideas. The coincident detection of both gravitational waves and electromagnetic light, like gamma rays, X-rays, visible light, radio waves from the binary neutron star merger event, GW177817, that was huge.
Why was seeing both signals together so important?
Because it showed that gravitational waves travel at the speed of light to an incredibly high precision, like better than 1 part in a quadrillion. Many of these modified gravity theories actually predict that gravitational waves would travel at a slightly different speed than light, or maybe follow different paths through space-time. The sources state pretty explicitly that this single multi-messenger event was enough to rule out specific, prominent modified gravity theories like Bekenstein's TeV model as comprehensive alternatives to dark matter. They just couldn't match that observation.
Wow. So detecting that one neutron star merger effectively closed the door on a whole class of modified gravity theories as a full explanation for cosmic anomalies. That's powerful.
It's a very strong implication derived from that key observation, yes. It really bolstered the case for dark matter being actual stuff. Now, beyond searching for primordial black holes and ruling out some alternatives, dark matter itself could potentially leave a subtle signature on the gravitational waves produced by merging objects like black holes or neutron stars.
How would dark matter influence a gravitational wave signal itself?
Well, if dark matter particles are densely clustered around, say, a merging binary black hole system, as you might expect if dark matter interacts gravitationally,
Right, gravity pulls it in.
then that dense environment could subtly alter the gravitational field compared to a merger happening in a vacuum. And that change in the gravitational field would thus alter the waveform, the precise shape, the wiggles of the gravitational wave signal that we detect here on Earth.
Okay, what kind of alteration?
For typical cold, collisionless particle dark matter, this dense environment could potentially cause a detectable dephasing in the waveform, basically shifting the timing of the wave's oscillations slightly over the course of the merger compared to what you'd expect without the dark matter. It's like dragging on the system gravitationally.
A subtle timing shift.
Exactly.
Yep.
And for other types of dark matter, like ultralight boson dark matter, sometimes called fuzzy dark matter,
Oh, yeah.
it could behave differently. These ultralight particles could potentially form a large, stable cloud or condensate around a spinning black hole through a process called superradiance. This cloud could then potentially emit continuous, almost perfectly monochromatic gravitational waves at a specific frequency something detectors could search for. Or these clouds could contribute to a diffuse background of gravitational waves across the whole cosmos. They might even affect the growth and mass distribution of the black holes themselves over cosmic time, maybe creating gaps in the observed population where superradiance is efficient.
So in the future, as gravitational wave detectors like LIGO, Virgo, KGRA, and upcoming ones like LISA or the Einstein telescope become even more sensitive, they could potentially act as indirect dark matter detectors by observing how dark matter influences space-time around these extreme objects.
That's exactly the hope. Analyzing these subtle environmental effects on gravitational wave signals is really becoming a new, exciting avenue to try and distinguish between different dark matter models and maybe even pinpoint properties of the dark matter particle itself.
It's clear the search is expanding in just about every possible direction, isn't it? Using everything from deep underground labs to mountaintop telescopes, and now these incredibly sensitive space-time ripple detectors.
It truly is. The era where maybe one single principle like naturalness strongly guided the search towards very specific particle candidates seems to be, well, it seems to be giving way. The new approach, as the sources emphasize, is genuinely this no stone left unturned strategy, exploring a vast landscape of possibilities across that immense range of masses and interaction types, and using every available tool, particle detectors, astronomical observations, and gravitational wave interferometers, all hands on deck.
And this includes continuing to push the limits on those older search ideas too, right? We're not just abandoning WIMPs entirely.
Oh, absolutely not. It's not that the old avenues are completely abandoned. For instance, continuing to push WIMP direct detection experiments until they really hit that fundamental neutrino floor.
The point where neutrinos from the sun or atmosphere start looking like WIMP signals?
Exactly. Hitting that floor is still really important to fully explore those original ideas. But the overall strategic shift is definitely towards diversifying the effort in a major way, with astronomical surveys and gravitational wave observations playing increasingly central complementary roles in the overall strategy.
And with this flood of data coming, especially from astronomy and gravitational waves, it sounds like we're going to be drowning in information.
We are. And the sources rightly point out that this shift towards a much more data-driven multi-messenger approach absolutely demands sophisticated analysis tools. We can't just look at it all by eye. This is where the booming field of machine learning comes in. It's already being applied quite successfully, actually.
How so?
Well, for instance, helping to identify potential WIMP signals buried deep in noisy detector data, or to automatically search through the vast astronomical images from surveys like LSST to find gravitational lenses, or even for real-time detection and classification of gravitational wave events as they happen. Machine learning, AI, these tools are going to be absolutely essential for sifting through the sheer avalanche of information we expect to receive in the coming decade from all these new instruments.
So wrapping this up, what does all this mean? It really seems like the quest for dark matter is in a period of incredible dynamism, maybe even a bit of upheaval.
I think that's fair to say, yeah. The theoretical compass provided by ideas like naturalness, which strongly pointed towards specific candidates like WINCs for a long time, hasn't led to discovery yet, at least not the simple versions.
And the field is clearly pivoting, as you said, towards this really expansive, no stone left unturned approach. It's opening up the exploration to basically everything imaginable, from ultralight fuzzy dark matter behaving like a wave, all the way up to massive primordial black holes, and pretty much all scales and types of candidates in between.
Right. And what's particularly fascinating here, I think, is the dramatic diversification of the experimental toolkit itself. It's moved far beyond just particle physics labs underground. Leveraging the unprecedented data that's coming from upcoming astronomical surveys and this entirely new window opened by gravitational wave observations, that's becoming absolutely essential to probe dark matter's properties on cosmic scales and through its gravitational interactions.
And navigating this data mountain relies heavily on tools like machine learning, as you mentioned.
It has to, yeah.
So this raises an important question, I think. If the nature of dark matter is turning out to be something that requires such a diverse, maybe even disparate array of probes spanning everything from deep underground particle detectors to mapping galaxies across the cosmos to listening to the faint echoes of merging black holes, Does that fundamentally change how we should think about its connection, or maybe its lack of a strong connection to the known particles and forces of the Standard Model? Does it feel more separate now? What stands out to you most about this rapidly evolving search?